Hi everybody, welcome to Mathematical Systems number 3, and this is the video. It starts for section 13.2, and today we're going to talk about rotational symmetry, and groups. And a group, or groups, are a mathematical term for certain kinds of mathematical systems. So suppose you have a four-pointed star like I've drawn here, not a very nice star, but a star nonetheless. And suppose what you want to do with this star is you want to begin to rotate it. And what you do is you only rotate in one direction, and we'll say it's clockwise in this case. And if I rotate clockwise a quarter turn, then star point number 1 will end up in this position right here. And then if I rotated it a half turn, star point number 1 would end up here, etc. Rotate it 3/4 of a turn, and if I rotate it a full turn, it'll end up where it begins. So if I go ahead and I number these points, or I label them in some manner, or color them red, blue, green, and yellow, something like that, then what happens is I can keep track of these starred points as they are being rotated. And because I can keep track of these starred points, that helps me to know whether these starred points, where they're going and where they're at in each case. And that's a very nice thing, because what does this mimic? Do you have an idea? Think about it. What's this mimic, this star being rotated? That's right, this star mimics our light switch, which had an off, low light, medium light, and high light that we also rotated, but it had 4 positions. So these are equivalent mathematically. And even though I'm rotating star points, I could rotate to a different position. Now, what we tend to like to call this is a rotational symmetry. And in this case, it's called a fourfold rotational symmetry. If we'd had a 5-pointed star, or a light switch with 4 settings for the beams, it could be a 5-fold rotational symmetry, etc. And so we can talk about M-fold rotational symmetries. In fact, if you wish, if I were to draw a square, like this, then that square has a 4-fold rotational symmetry, just like the star, or just like the light switch did. So what we'd like to do now is we would like to define a concept called a group. And after we do this, then we're going to do a little bit of a problem, or a number of problems, and then we'll go through that. So what is a group? Well, a group has 4 properties, all right? And property number 1 is that a group is closed under its operation. So it's closed under its operation. Now, that operation could be a little circle like we used before. It could be this kind of modulus plus, or this varied multiplication. And so you can make all kinds of symbols for operations. In fact, the operations could be just our normal add, subtract, multiply, and divide. And so something is a group, number 1, if it's closed, has closure. Number 2, something is going to be called a group if it is associative under its operation. So I'm going to use a little circle here to represent the operation, but even though I'm using little circle to represent the operation, it could be any other specific operation. Now remember, it's a group using one operation in one set. All right. Number 3 is the set of elements will have an identity, and there will be just one identity that works for all the elements under that given operation. And then number 4, the inverse of each element lies in the group as well. So what we have is what we like to call in mathematics, we like to call a structured set. This is a very structured set. It has lots of nice features. It has closure, it has the associative property, it has one identity that works for every element, and each element has its own inverse. So this is a structure imposed on this particular set. And if a set has structure, it can do things. All right? Now, if it has a 5th property, which is the commutative property, if a group, already we've decided it's a group with those 4, but if the commutative property works as well, then we say it is a commutative group. And so therefore there must be non-commutative groups. And so your goal on these examples we're going to do is to show that a mathematical system actually creates a group. So now we're going to do an example, and we want to show that A is a group over the operation little circle. So here's our example. We have a set A, which is the element 0, 1, 2, 3. We want to define our binary operation, little circle, so that A little circle B is the remainder when you divide by 4, and I should have said divide the sum by 4. So if I say that, now I've said it correctly. And what I want to do then is show that A is a group over little circle. Okay? Now to do that, I have to do the 4-step process. And so to help myself do this, I am going to draw the table for little circle, and where I do this sort of crazy operation where I add the numbers and then divide them by 4. So I add them and then divide by 4, and I then record just the remainder. And when I do this, I end up with this table the way I've written it here. Or, excuse me, it's not going to let me do that. Sorry, I wrote it not quite correctly. Got to put 1, 2. Okay, so now I've made a table with this operation. Now, if I had a lot more elements, these tables get longer and longer, but we've seen this one before. It's the light switch problem. It's actually a rotational group as well, and it's also this kind of funny addition where we add them up and divide by how many elements there are and record the remainder. Now, when I do that, is this going to be a group? So number 1, the question is, does it have closure? And I have to be able to answer that question, but what I see is that no matter what elements I combine, when I look at all the elements here, what I see is I see just the elements I begin with. So by closure, I can say, well, if I have A operated on B, that's going to be an element of set A. And I can see that no matter what A or B is, whether it's 0, 1, 2, or 3, it's always going to be an element of set A. So therefore, I have closure. So let's go to number 2. Do I have the associative property? Now the associative property is the hardest one because you have to show A operated on B operated on C is equal to A operated on B, regroup it operated on C. And the only way you can do that is take all combinations of 3 of these numbers and then check them all. Now there's a lot there, so my suggestion is you check 1, so pick a combination, for instance like 1 operated on 2 operated on 1, like that, and then set that equal to 1 operated on 2 operated on 1. So pick some combination and try it out. Well, now I can do this. 2 operated on 1 is 3, and now I have 1 operated on 3, so 1 operated on 3 is 0. So this side over here is 0. And then I'm going to check the other side. And the other side is 1 operated on 2, and I get 3. And then I do 3 operated on 1, and 3 operated on 1 is 0. And this makes sense. If we think of it as a rotational group, what we're saying is if we start at position 2 and go one more position, we're at position 3. And then if we rotate it one more at that point, then we're going to be at position 0. And you can do the same thing with the other side. Think of it as a pinwheel or a little star rotating. So I know it's true for this one. So the real question is it true for all of them? And the answer is, since I'm adding these numbers and just recording the remainder, you can resort back to just arithmetic to say that A operated on, or A plus B divided by 4 is always going to give you a remainder of 0, 1, 2, or 3. Therefore, it's going to be associative. Okay? So that's kind of hokey, but it gets you to where you want. So number 3 is there one identity element? In other words, if I combine A with something, do I end up with A? So if I combine 0 with 0, I end up with 0. So that's nice. Well, if I combine 1 with 0, I end up with 1. 2 with 0, I end up with 2. Well, you get the idea that the identity, and we usually label that I, is equal to 0, and that it's the identity for every element. And so you could, if you wanted, then say A operated with I, or 0, equals 0 operated with A, which will always equal A for all the elements. So the next question is, what's the inverse of every element? And so just as we've done before, you have to find the inverse, and the inverse you have to go looking for it. So what we did in the last lesson is you want A operated with something, so you end up with the identity, which is 0. So what's got to go in that box? Well, 0 operated with 0 gives me 0, so that's true. So now I'm That's true. And 1 operated with 3 gives me 0. And 2 operated with 2 gives me 0. And 3 operated with 1 gives me 0. So in other words, the inverse of 0 is 0. The inverse of 2 is 2. The inverse of 3 is 1, and the inverse of 1 is 3. So every element has an inverse. Therefore, this has the inverse property, and this is a group. And so now, since we know it's a group, you are ready to do problems 2, 3, and 5 through 19 on page 765. Now, in class, I'm going to do another example of this. But for your quiz, when you get to class, I'm going to ask you, what is a group?